Chapter 5, Quadrilaterals. Today we're going to look at Section 5.2, Ways to Prove that Quadrilaterals are Parallelograms. 5.2, Ways to Prove that Quadrilaterals are Parallelograms. Objectives. After studying this section, you'll be able to prove that certain quadrilaterals are parallelograms. Your class opener for today. List 4 properties of a parallelogram. By definition, if both pairs of opposite sides of a quadrilateral are parallel, then the quadrilateral is a parallelogram. So we're pretty much using the definition of a parallelogram. If you see that the left and the right sides are parallel, and you see that the top and the bottom are parallel, you know that the quadrilateral will be a parallelogram. So let's look at some other ways to know if something happens to be a parallelogram. Theorem 5.4 says, if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So if you have a 4-sided shape and opposite sides happen to be congruent to one another, you know that the shape is going to be a parallelogram. Theorem 5.5. If one pair of opposite sides of a quadrilateral are both congruent and parallel, then the quadrilateral is a parallelogram. So this one doesn't deal with both sets. If you can just get one set of opposite sides parallel and also congruent, that's enough to show that it's a parallelogram. And it doesn't matter which set of opposite sides, if it was the top and the bottom, or if it happened to be the left and the right. Theorem 5.6. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So this is similar to the opposite sides. If you can get both pairs of opposite angles congruent to one another, then your quadrilateral is going to have to be a parallelogram. And we have one more way to show that something could be a parallelogram. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So imagine drawing in the diagonals. We know that the diagonals aren't necessarily the same length as each other, but if we do know that they happen to be bisected, so we know that the pieces are congruent to each other, then we know that we have a parallelogram. So, quick review. Here are the methods that we have for proving that something is a parallelogram. We either have opposite sides are both parallel, we have opposite sides are both congruent, we have one opposite pair of sides both parallel and congruent, we have both pairs of opposite angles congruent, or we have that the diagonals end up bisecting each other. So let's look at some problems. Study the markings on each figure and decide whether ABCD must be a parallelogram. If the answer is yes, state the definition or theorem that applies. So number 1, right away I noticed that the opposite sides in this parallelogram are congruent, and if opposite sides are congruent, then we know that the parallelogram, or that the quadrilateral, has to be a parallelogram. So this one would be yes. Number 2, I see that opposite sides are parallel. I see that opposite sides are also congruent, and that was one of our theorems. If you have opposite sides both parallel and congruent, that it is going to be a parallelogram. So this is another yes. Looking at number 3, I see that opposite sides, or one pair of opposite sides, are congruent. I see that one of the diagonals gets bisected. That's not enough information to show that something's going to be a parallelogram, so this is going to be no. Number 4, if I look, I see that the diagonals were bisected because the pieces are congruent, and that's one of our methods. If diagonals are bisected, that you have a parallelogram, so that's a yes. Number 5, I have one set of opposite angles congruent, but I don't know about the other ones. And since I don't know anything about the other angles, I don't know if it's a parallelogram, so this is also no. Number 6, I have one pair of opposite angles congruent, and I know that the other one is 110, but I still don't know how big C is. But I do know something. In a quadrilateral, all the angles have to add up to 360. So if I take 360, subtract off the 70, the 110, and the 70, I will be left with 110. And now that I have opposite angles congruent here as well, both pairs of opposite angles are congruent, so I do know that this is a parallelogram. Looking at some other problems. Number 7. I noticed that opposite sides are parallel, and I noticed something else for this one. I noticed that I have two 90-degree angles. Well, what that tells me is I have two lines that are both perpendicular to the same line, and if they're both perpendicular to the same line, they also need to be parallel. So I know that DA and CB are also going to be parallel, and with both pairs of opposite sides parallel, I know that it's a parallelogram. Number 8. Let's see. I see a set of alternate interior angles are congruent, which will give me the top is parallel to the bottom, and the left is congruent to the right, but that's not enough information to show that it's a parallelogram. So this one is no. Number 9. I notice that I have some alternate interior angles congruent, which is going to let me know that the top is parallel to the bottom. I have another set of alternate interior angles congruent, which is letting me know that the left and the right are parallel. And since both pairs of opposite sides are parallel, I know that it's a parallelogram. Number 10. Draw a quadrilateral that has two pairs of congruent sides, but that is not a parallelogram. So two pairs of congruent sides, not a parallelogram. The one important thing that's missing is they don't say that they have to be opposite sides. So I could draw a shape that looks like this, where these two are congruent, these two are congruent. So I have two pairs of congruent sides, but since they're not opposite, it's not a parallelogram. Number 11, draw a quadrilateral that is not a parallelogram, but that has one pair of congruent sides and one pair of parallel sides. And this can be done just because it's not the same set. So I'm going to draw one set parallel, and then the other set of sides are going to be the two that are congruent. Now, if it was the same pair of opposite sides, parallel and congruent, it would have to be a parallelogram. But if I split it up between them, it doesn't have to be. Proof theorem 5-7. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So let's look at our figure off to the right. I know that we're going to have to draw in diagonals bisecting each other. So we can do that. Then let's label all the vertices. And let's start to fill in our proof. It says that the diagonals bisected each other. And I know if something gets bisected, it gets cut into two congruent size pieces. So let's start to write down. So I know that segment AC bisects segment DB. And likewise, segment DB bisects segment AC, and that's going to be our given. Trying to prove that it's a parallelogram, I'm going to try to get opposite sides being parallel. So if I can show that the triangle on the left is congruent to the triangle on the right, I can get alternate interior angles proving that the left is parallel to the right. Likewise, if I can show you that the triangle on the top and bottom are congruent, I can get alternate interior angles to show that the top is parallel to the bottom. So that is our main plan. So to start, I'm going to state that since the diagonals were bisected, I have congruent sized pieces. So I know that segment AE is going to be congruent to segment CE, And similar to for the other diagonal, that segment DE is going to be congruent to segment BE, and that's all by the definition of a segment bisector. Now, to get the triangles congruent, I'm also going to need some angles congruent. And to make things a little bit easier, I'm going to come in here and number them. Angle 1, 2, 3, and 4. So I know that angle 1 and 2 are vertical angles, and that they're going to be congruent. And I know that angle 3 and 4 are vertical angles, and that they're going to be congruent. And then I can get that the triangles are going to be congruent by side angle side, whether they're the yellow triangles or whether they're the blue triangles. So I need to state that angle 1 is congruent to angle 2, and that angle 3 is congruent to angle 4, and our reason is going to be vertical angles are congruent. Now I can get the triangles are congruent. So the yellow triangles, triangle ADE, is going to be congruent to triangle CBE. And I get the blue triangles, so I'm going to get triangle ABE is congruent to the triangle on the bottom, which is CDE. And the reason for both of those is going to be side angle side. And now I'm going to go for the fact that I can get these alternate interior angles congruent, which will give me the left parallel to the right. And then in the blue triangles, I also have alternate interior angles congruent, which gets the top parallel to the bottom. So starting with the angles marked in the yellow triangles. Over on the left I have angle ADE is congruent to angle CBE. And in the blue triangle up in the top I have angle BAE is congruent to, down in the bottom it would be DCE, and we know that the reason is corresponding parts of congruent triangles are congruent, which we write down CPCTC. Now if the angles are congruent and there happen to be alternate interior, I can get that the opposite sides are parallel, so I can get that AB is parallel to DC, and at the same time I can get that AD is parallel to BC, and our reason is if alternate interior angles are congruent, then we get parallel lines. And then we're up to our last thing we wanted to prove, which is ABCD is a parallelogram. And this is going to be by the definition of a parallelogram, since we have both sets of opposite sides parallel. Your closure for today then. List the 5 ways to prove a quadrilateral is a parallelogram.